Okay, well, finally, let's do an example. Okay, well, here's our example. Imagine we have a beam of electrons traveling in a conducting pipe, which is at voltage 0. So these electrons are in a potential energy environment of 0. Then they're going to make a transition to a second pipe, which is at an electric potential of minus 3 volts. Okay, so to enter that pipe, and then within that pipe, the electrons will have a potential energy of plus 3 electron volts. All right. So here we have electrons. We'll give them a kinetic energy of 4 electron volts for the incident electrons. And then they're going to enter a region where the potential energy is equal to 3 electron volts. And we'd like to find out what the probability of reflection is. All right? Okay, so remember, the electrons are defined by their K values in each region. In region 1, the kinetic energy of the electrons is 4 electron volts, and K is equal to 2 me over h bar, okay? In K2, in region 2, we have 2 me minus u0 over h bar. Well, we know they're electrons. We know the energies. We know the potential step. We have everything we need to do the calculation, right? Well, we do. But in fact, if we're clever, we can simplify this problem quite a bit and find our answer quickly. Here, let me illustrate. We know that the reflection coefficient little r is K1 minus K2 over K1 plus K2. But when we look at K1 and K2, we can see that they have many constants in them that are almost the same, okay? So that makes us think that it would be helpful to rewrite this. Let's divide the numerator and the denominator by K2. What do we get then? We get K1 divided by K2 minus 1 divided by K1 divided by K2 plus 1. Okay? That might be a nice way to approach this problem, because then we only need to figure out what K1 over K2 is. All right? And you can see that this is square root of 2me divided by h bar divided by square root of 2me minus u divided by h bar. And what's nice about evaluating this is most of the terms cancel. So we just get square root of e over e minus u0. Okay? Oops. Well, and this is just the square root of 4 EV over 4 minus 3 EV. The units cancel, and we just have square root of 4. So coming back then, R is equal to 2 minus 1 over 2 plus 1. So it's 1 over 3. Okay, so the relative amplitude of the transmitted wave is 1/3 the amplitude of the wave function in region 1. We wanted to find the probability of reflection, capital R. which is just little r absolute value squared. And you can see this equals 1/9. There we go. So we've done it. For this particular problem, we've evaluated the reflection coefficient for the particles, and we found 1/9. All right? Perfect. That wasn't so terrible, was it? 1 second. All right. Here, let's do a second example. It's the same setup now with the same electrons, only now we've raised the barrier potential to -5 volts, so that the height of the potential step is 5 electron volts, whereas the electrons only have a kinetic energy of 4 electron volts when they enter the system. Well, now we want to look for barrier penetration. So let's consider this problem and see if we can find delta, the penetration depth. All right? So we know that K2 is given by this expression here, which means that alpha is 2m times u naught minus e over h bar, okay? And delta is 1/alpha. So K2 is fine, but it's an imaginary number. Alpha, we've switched the numbers around, so we'll get a real number, and delta is 1/alpha. So then alpha is equal to, well, the square root of 2 times the mass of the electron, 9.11 times 10 to the minus 31 kilograms, times E minus U. So that's U minus E. So that's 5 minus 4, or 1 electron volt, or 1.602 times 10 to the minus 19 joules. Okay? And all of that divided by h bar, 1.054 times 10 to the minus 34 joule seconds. Okay? That's alpha. We just have to figure out what that is. All right? And, well, now we need to spend a minute with our calculators. Okay? So, plug away. And when you do this, you'll find that alpha is equal to 5.13 times 10 to the 9th inverse meters. Okay? And of course, what that really means is that delta, which is 1/alpha, is 1.95 times 10 to the minus 10 meters. Or delta is about 2 angstroms. Okay? So in the problem we've just found, electrons will penetrate into the forbidden region. They don't penetrate very far. They penetrate about 2 angstroms. That's on the order of the size of an atom, right? Because of that, you might think of a picture that would go along with this. Okay? Actually, we have electrons in this pipe. And we might imagine that the electron wave functions, or cloud, sort of penetrates a little bit beyond the edge of the tube. Okay? But only a few atoms worth. In any event, what we've just found is an expression for barrier penetration for this particular case. All right? Barrier penetration is a phenomenon which doesn't occur in classical mechanics, so it's really interesting to see it and work with it here in this problem. All right, let's stop here, and I'll see you in class.